Hi, good morning. First of all, thank you to all the sponsors for supporting an initiative like this. I think it's great that organizations like Keystone, UNESCO, and so many others who have come together to create a combined platform to discuss, what concerns us all. How do you conserve? How do you preserve something for the future? It's intimidating to do a 4.5 billion year history in 45 minutes, but I'll try my best to do that. So I'm going to try, putting in, combining what I know about the Nilgiris after having read, works of so many brilliant scientists who don't come forward sharing the immense wealth of knowledge that they have, especially people like geologists, paleontologists, hydrogeologists, geomorphologists, all those kind of people. So I want to basically look at how I want to introduce the whole geological journey of the Nilgiris. And I also want to, actually impinge on the next two sessions that are going to happen. What is it that the geological information can inform in terms of better management? Or I don't think this is a good word, but how do we plan for the future by looking into deep past, right? And there are several lessons that I think that can be drawn from that. So I think this is a kind of a map that we see, right? Topography and, elevation and sometimes also aspect thrown in. There's actually a place in Kerala which is minus 11 meters. The deepest place is, I don't have it here, but it is right here, quite close to the to the coast of, which is natural, right? The deepest place, of course, in the world is Dead Sea, but in India, it's only 11 meters. But the thing that I'm trying to show here is that you've got a chain of mountains, which Professor Sukumar spoke about so eloquently. I'm going to talk about only the province of the geological province of the Nilgiris and how they are related. So geologists generally show a map, something of this kind, right? You've got fabulous amount of colors. All of them are types of rocks that were made in different times. And the origin of these ancient rocks comes from one type of rock, which is the basalt. So everything was volcanic. Everything came out of magma when the earth was molten. Now, just to put it very simply, let's imagine that we've got a broth of soup. Let's imagine tomato soup, right? You've got a tomato soup which you're drinking from, perhaps consuming. You're a cook and you've got the broth put on the fire and you're just tasting it regularly, right? Just to see if it's getting right or not. Now, as the soup is getting cooked, it's getting thicker. Now, imagine that soup's taken when it's nice and hot and it's taken and served to somebody, right? Somebody who's going to consume it. And that person puts croutons. Now, croutons are basically those bread cubes, right? That are put onto it. Now, the reason why I'm telling you this story is that sometimes the magma, when it cools suddenly, it creates a blob on top. It floats on the magma. Now, what actually happens is that magma has so much energy that it pushes rocks that it itself has made. It's got congealed, it's got accreted, it's actually come together to make a bit of a ball, right? Now, those rocks get heated and reheated again and again, and sometimes get drawn down back into the magma, where it gets cooked and recooked. Now, these are the colors that you get after cooking and recooking. Sometimes two different blobs joined together to create a new kind of a mineral, right? A new kind of a rock. Now, remember that we're talking about a period between, 4 billion years and 550 million years. So you've got 3.5 billion years of rocks that are shown here, right? Our area is this, Nilgiris, right? It's separated by the Coorg block, which is the oldest rock in India, right? About 6 years ago, geologists discovered a certain part in the Coorg hills that was roughly 3.6 billion years old. It's among the oldest in the world, right? But if you notice that the rock is shaded turquoise blue, if I can say that. Is that the color? Yes. Let's say teal, right? I mean, if people are finicky about colors. So the teal color is there in Nilgiris as well as in Coorg, right? You've got this as a family of rocks that emerged together, roughly between 500 million years, right? 500 million years is what's taken for both these blue rocks to form together. That means the oldest part, that is somewhere here, there's one tiny rock which is older. The rest of them kind of came together around them to make this block together, Coorg and Nilgiris. But then something more interesting happened. Now, this is the detail, right? So the teal color is just come back as, let's say, dull green, because this is from a different map. So I've just blown that up. You've got other smaller specks of rocks that have come up. Now, where is the crouton story going is what you're asking, right? Now, this is a part of the crouton because it's gone down and come back again. But sometimes when the crouton goes down, it picks up other specks. Now, these are the specks that I'm talking about, right? These tiny specks of new types of rocks that emerged many times over during the cooking and recooking of the rock. Think about it. The earth is restless, right? Now, what we've been thinking and what we imagine the earth to be restless is in the form of landslides or avalanches and things like that. But beneath the surface of the earth, when it was really, really hot, I mean, you had magma which was not so deep down as it is today. It was really, really hot, and magma used to come out in the form of volcanoes and even open fissures that would release magma, right? The other thing that could happen was giant meteors would come and crash into Earth and create deep fissures that would release magma. Now, there are two meteor sites in the world that are not depressions, but actually they are mountains that have been created because the magma came out. And one of them is in India. And those of you who've read my book, I talk about it. It's a place called Dhala. It's near Shivpuri. And Benno, I think it should be a geological diversity site. I know you at UNESCO, you have these wonderful programs looking at geological diversity. I forget the term. But here's a unique site. Instead of creating a depression, a crater depression, it actually rises up. So this kind of a condition of bringing the magma up was constantly, raising plateaus that were formed like this one. But as those plateaus were being formed, you had smaller fissures that were releasing minerals and new types of rocks. Notice near Gudalur, there's a stream here, and I forget the name of the stream. It's not too big. It's perhaps this wide. It was notorious for elephants coming in the afternoon to have water. So we were warned, be very careful. And if you notice the color here, it says gold-bearing quartz veins. You actually get them. If you're interested, go down to that stream and you would find quartz and specks of gold. Very tiny, not economic, of any economic value, but it's just the fact that it has such amazing variety of minerals in it, right? Even sapphire. Sapphire, when it breaks down, is called sapphirine. And you find sapphires as well. So you have quartz, you can make beautiful pendants. I mean, young ladies here, go out, because my daughter does that, right? So although, as non-geologists or people who don't look at rocks, we find them very boring, there are amazing histories that exist in landscapes that we find with what we think are boring, but they're not. There's amazing, amazing ways to look at rocks. All you need to do is look at it carefully, try understanding the history, and there is an amazing story that each rock will tell you from this region. I think the Nilgiri Biodiversity Reserve uh, uh, biosphere reserve, is also a heritage site in terms of geology. It's an amazing place because you have such, not just landscapes, not dramatic hills and whatever, but also the amazing amount of minerals that it has to show for itself. I'll just move very quickly because I know we are running out of time. So how did Nilgiris rise up? How did it get created? Why is it an isolated hill? Why do you have Satyamangala on top, or the BR hills there, or the Kurg? What creates the Moyar, right? What creates the fact that each hill system got separated? Now I'm I'll attempt to tell you the story in as less complex a way as I can. Imagine that there is a crouton. You remember the bread, piece of bread that was floating on top of the soup? Imagine this to be the soup. Okay, this yellow part is your soup, and you've got one old crouton that's got burnt, it's heavy, and it's come out, right? And as the soup is cooling down, it has a thicker layer, right? Soup becomes thick, right? But there is heat here. The earth is still hot, but as it's cooling on top, there are other things that are forming. I mean, it can be like cream or whatever you want to call it, a creamy layer on top, whatever. But this movement of this block is the one that's pushing the last remaining fluid on top towards another crouton. They're going to jam together, and they're going to join together. Now, another side story. How did Earth get water? Does anybody know? It came from meteors. 80% of the world's all the water that has arrived on land is through meteors. The rest of it is because of volcanic movement. The movement of magma, the creation of minerals, and water was a side product, right? So this water that is there, which is overlaying the mantle, which is extremely hot, it's like a hot tin plate on which you've got water, right? And this is the place where the minerals will interact and create new types of other rocks, because rocks that are created with water and those devoid of water are slightly different. The temperatures are different, pressure is different, and the composition, because you get extra hydrogen and oxygen. Water, as everybody knows, is H2O, hydrogen and oxygen. Rocks here would have fewer oxygen and hydrogen compounds. Those created in the oceans are more rich in both hydrogen and oxygen, right? Now, as this is happening, you have ocean plates. I mean, I'm calling this plate, I think it's a crude term, but this zone is shrinking, right? But beyond a point, the movement of the mantle, which is pushing the mainland on top, and the volcanoes that are still spewing out the magma, which is coming out, it produces new and new types of rocks. But under the ocean, there's another type of rock, right? Now, imagine this to be like Indonesia or Philippines or Hawaii. This is how the system looked like, or this is how Nilgiris looked like about 3.5 billion years ago, right? For 1 billion years, the Nilgiris was like this. So it was like the Philippines or Indonesia or Aleutian Islands, or one of those active, or Kamchatka. We had this major eruption. The process of pushing the landmass further and raising these volcanoes, and beyond a point, this plug, this reservoir of magma gets choked, it gets shut, right? And as a result, your volcanoes are no longer volcanoes, they become dead mountains, right? And you have this part under the volcano starting to cool down. So imagine this to be like a pimple, right? All of us had pimples in our teenage years, or those who are about to be teenagers would know what this is. That, as soon as your pimple starts to dry up, you have a bit of a deposition. It becomes a little tender under the pimple, right? So this place is tender and deep, right? And so that tender part is the one that is actually creating the solid rock, which is going to be a basement rock. And what happens is that the collisions start to push that basement up. You know, the rock here has started to congeal and form into a solid rock. And you've got different types of rocks here. I'm going to show you what they are so that the next time you're driving past, you would know what they look like, right? Now, let's look at it another way. Let me show you another cartoon. So let's look at what was happening to the islands, the volcanic islands that we were talking about, right? So this process of movement where a plate buckles under another, right? So it's a little like driving in India, right? You've got a car which is bigger, or you've got a bigger truck versus a person who's driving a small car versus a person who's driving a scooter versus somebody who's driving a cycle. So you boss with one another, right? You try taking each other's space. This is exactly what's happening here. So if a layer which is more dense, it does not give space or way to something which is lighter. So as a result, it has to, succumb to the pressure and, buckle under the more dense plates. So this is called subduction. It goes down, right? So this is the sea level that is called the oceanic crust in grain color, this one, right? It starts to go under an island which is already very, very well established. It's dense and it, absorbs the pressure. This is the process that would have happened 50 million years ago when India collided with Eurasia, right? When the Himalayas started to form up, right? So this is the process. But as the volcanoes are brought closer to one another, they tend to weld together. They come together and become one. And this is what happens here, that one volcanic chain joins another. And together you have a series of volcanic islands that are forming, and they create what is called a continent or a landmass like continent, right? So this is how the Nilgiris got created. We are actually sitting on volcanoes that are in deep time have got extinct and then got plugged. They are no longer volcanoes. There are very few signs to say that they were volcanoes, right? Now, this is a complex cartoon, but once you see the beauty of it, you will realize what I'm saying. Now, if you see here, this is Gujarat, and this is the Indian subcontinent, peninsular India. And here you've got the Mahanadi, the course of the river Mahanadi. And this is the Eastern Ghats. This is where the Kaveri suture is. And this is Achinkovil, right? And this is Madagascar, right? And this is Sri Lanka. This is Australia and part of Antarctica. And this is Africa. Okay. Now this cartoon is basically covers a period from 3 billion years ago to about 500 million years ago, right? So it's a very large span of time. It talks of a time when the earth had started to cool and the first signs of life had emerged. And it also ends at the time, which is 500 million years ago, when multicellular life had emerged. So this is the span of time. It's huge. So it takes 2.5 or maybe 3 billion years before the first life starting and multicellular life starting. It took 3 billion years. Okay. Now, why is this important? The reason this is important is it shows the connection of the rocks from Madagascar to Achinkovil to Sri Lanka into Australia. Notice that Madras, which is here, Chennai, which is here, and Perth, which is here, they're very closely related. The rocks are very similar. And perhaps that's one reason why both these countries or both these cities have very good fast playing cricket pitches, right? I mean, they both have, And of course, we didn't, the creatures that lived at this time did not need a visa or a passport or whatever to cross over. I mean, it is, this arrangement is going to stay together for about another 100 million or 150 million years. Around 400 million years ago, this is, when it says 0.55 GA, it means 500 million years, right? Or half a billion years. About 400 million years ago, the land masses tend to start separating, starting from here. Africa separates from Australia. From below, it's unzipping itself, right? Madagascar and India stay together until 88 million years ago. It's only as recent as that, only 88 million years ago, right? I know it sounds funny, only 88 million, but in geological time, it's very recent, considering you're talking about 4 billion years, right? Let's look at the rocks that got created. So if you were to dig here, chances are you're going to see this layer, right? Starting with the top is the laterite, right? It's the orange color that you see all the time, right? Just below it is also another orange colored rock, which is this, right? It's a very common rock. If you look at a landslide or a landslip or even construction along the roadside, you find these conglomerated laterite with other calcium-rich, limestone-based rocks that have been formed with very mild heating. And it is a very, very fluid structure. This is the reason, one of the reasons why we have a problem with landslides. I'll come to this in a bit more detail on how we need to manage it or what to look at it, right? Let's look at the next rock. It's called dolerite, and it occurs with another volcanic rock called gabbro. Now, you can look at the difference in the colors. You can look at the size of crystal. Gabbro has big, thick crystals. Dolerite has thin, sugary crystals that have been packed together. Both of them are pretty hard rocks and quite easy to spot. They generally tend to occur together in this region, but nowhere else in the world. Very few places, I wouldn't say that, nowhere else in the world, but dolerite and gabbro tend to exist quite commonly here together. The next rock, which is perhaps the most abundant rock here, and I think the most defining rock of the southern peninsula India, is this rock called Charnockite. It's named after the man called Job Charnock, who was the founder of Calcutta. He's a master planner of cities, and helped create Murshidabad and Burdwan and several cities. If you go, you find a statue. This got named after him because his graveyard in Park Street in Calcutta was made with this rock. So it got called Charnockite. It's not because he discovered it or he did anything with it. Now, Charnockite exists in this region with another rock called hornblende biotite. Now, I won't go into those details of what their minerals are and what they are. It's very boring. I mean, it's really boring. So let's not get there. It's too much of chemistry involved. The reason why I'm showing this to you is because you can understand the layers that are involved. I'm starting from the bottommost, because Charnockite comes on and off in this region. This is a very important rock if you want to understand this region well, especially in terms of landslides, stability, and movement of water. It's a critical rock. The reason why I say this is because it's called fissile hornblende biotite. Nice, very long name. Characteristic of the Bhavani group. The rock actually starts from, I think it's about 40 kilometers from here, Bhavani uplands. I don't know. Where would Bhavani is about 40 kilometers? Yeah. Yeah. So you find this rock there. It's a very shiny rock. And in some places, it's very friable. So if you drop it, it shatters. Okay. So it's a very important rock because it determines the stability on the land on which you establish anything. Whether you're building a canal or you're building a city or even a road, there are problems if you're crossing this thing. The next rock that is very useful to know is this rock. Now, it is a beautiful rock, has these red crystals or red grains in it, which actually lend it a very characteristic granite look, but very difficult to work on because it shatters very quickly. Unlike, say, the Kadapa stone or the granites that are found in Rajasthan, it's very stable. This is not stable, so it's not very good for quarrying. It's okay to use it for building foundations, but it's not very useful otherwise. And finally, the rock that is the champion rock is Charnakite with magnetite. This is again a new form of the hornblende. You remember I spoke about the hornblende biotite Charnakite. This one has more grain. It has other minerals that lend it slightly yellow and green color. So it's a Charnakite which is deeper and more embedded. Okay, if I were to cut through the rock, and most geologists would not approve of my showing this to you because they don't have a system to do this. But I'm taking the liberty, the artistic license to say, okay, if I were to cut through from say the southeast, which is say Metupalayam to Gudalur, right? If I were to cut the rock, what would I see? So basically, you've got granite, which is on top, and then you've got a quartz vein, which is here in between, and then you've got this yellow part, which is called nepheline cyanite, which is largely Charnakite, the Charnakite that we also see because of road construction that's exposed. And then you have the basement rock, which is a type of a granite with a gneiss. Now, gneiss is a very interesting rock. It is very easy to recognize because it's got a ribbon-like thing flowing across it. So if it's an intact gneiss, it has a ribbon. It's got a white ribbon going around it, and it's looks like a snake or actually a ribbon. So the two things that you need to take note of is this green part, which you see at the entrance. So if you remember, if coming from Metupalayam, there's a bump before the first bridge, right? I don't know if you've noticed so there's this theme park. I don't know what it's called, Thunder something. Black Thunder, is it? Yeah. So soon after that, there's a bump, right? And that is this. Sorry, the bump. I'm terrible at drawing, so please, this is an exaggerated bump, right? It's not such a big bump. It's actually much, much gentler. But the point I wanted to make is that that's the hornblende gneiss, which is a solid rock. But once you come here towards Gudalur, you have a problem because you've got granitite gneiss, which is exposed, and towards the top of it, you've got shales with limestone. Now, shale with limestone is a problem because limestone allows water to pass through. Laterite also allows water to pass through. Now, when that happens, and both these rocks are together, there is a problem because it can hold water only to a certain amount. And if it rains incessantly, both of them give way. I'll show you a case study about it. Now, let's do a quick recap of what 4 billion years look like. Okay, so first, the crust was forming. Remember the thickness of the soup, the croutons rising and all of that. So that's the point that's here, that the Nilgiris crouton rises through the thick soup. You get to see that. And then the basement rocks, the granitoid gneiss, starts to burn. It's like the crouton from below has burnt. When it sank down, it burnt, went down to the bottom of the vessel on which it was being cooked. It got overcooked and it came back again on top. It became the first basement rock. And then the roiling magma started to take these rocks back and forth into that soup. And it created the mix of rocks called the granulites. Don't get confused with these words because, geologists have this tendency to, give too many labels to the same thing, right? I mean, the same set of things. So don't get too perturbed. I hope no geologists here, they might take offense, but yeah. The next thing, that important aspect that happens is that the thickness of the soup increases. There's a lump in the soup that forms, and it gives the depth of the basement rock, which is a very deep basement rock in the Nilgiris. It's a great advantage to the Nilgiris to have that, but there is a disadvantage to it as well, which I'll come to a little later. Now, this thick congealed rock begins to accrete newer minerals around it, and then there is a long period of very little tectonic movement. There's nothing happening. The soup is stagnant. It's across southern India. There's no movement in the soup. Then, because there is collision between India and Africa and Madagascar, there's mountain building happening. And the first attempts of, or the first scarps of the Western Ghats rise. The Western Ghats don't exist. Coorg already was there. Agastyamalaya was already there, right? Although not as high as they are today. The height would be achieved much, much, much later. So Coorg's height and Nilgiris elevation would be achieved much later. But the Western Ghats begin to rise only after the Gondwana. Remember I told you about unzipping from below? That process of unzipping is the one that actually raises the Western Ghats. And then 68 to 65 million years ago, around the time when the dinosaurs are beginning to die, Deccan volcanoes burst just north of where we are today. But it has no impact, or virtually very little impact, on this terrain. There's some impact on Coorg, and of course further north, but nothing here. Now, when India, or the greater India, we've still not attached ourselves, we're moving at a great speed towards Eurasia, and we collide. We create stresses that actually raises the Western Ghats even further. So the Aravalis shrink because they fall, they lose their basement, and they kind of collapse. But the shock waves that are happening actually push Western Ghats up. All the margins begin to rise. The Eastern Ghats shrink. The Western Ghats rise. Okay? And the Western Ghats continue to rise, and their greatest rise happens very recently, only 20 to 10 million years ago. It's a very recent phenomena where you see the rise of the Western Ghats to the scarps that we see. So anybody here from Bombay, if you go to Badlapur, anybody here from Bombay? Anybody who's living in Bombay? Oh yeah, of course. But in Badlapur, there's a section where you can actually see the last 10 million year push that has happened in a single basement rock that has been lifted up. Okay, so it's only more recently that we've started to see the topography, the plateau comes into that, after having got bumped several times, it finally comes into the plateau shape. It's not in a full incline or a decline, but it's a plateau. And finally, you start seeing the sholas and the cloud forests and everything else forming only 25 to 10,000 years ago. That's the time when you have these mini ice ages that are happening. So the passerines, any bird watchers here would know that all birds that we see today, or most birds, I won't say all, they're hoatzins and even the flightless birds of New Zealand and other islands evolved much earlier, but the others evolved around 22 to 10,000 years ago. So there was a period before the 22,000 years where the birds were very different, right? They had their ancestors. All the modern crow, the sparrows and everything else had their ancestors, but the current species that we see evolved more recently. Okay, I just want to take you through the controversial thing that I said about how rocks can inform you about planning better, right? I think it's a crucial aspect. We know this elevation map. I think we can bypass this. We know this, most of us know this, it's the slope map, right? Where are the slopes? What are the elevations? And what is the degree of the slope? Then you have aspect. Where is your peak facing? Is it north, south, east, west? An important aspect because you want to see the flow of the rivers and the streams, and also the arrival of monsoons. How is it going to hit a certain hill, right? You want to see how does the monsoon arrive? Because the movement of the clouds, movement of the monsoons is depends on the orientation of not just your elevation, but also the bands that the monsoons create. Now, I'm going to come to this a little later, perhaps my last slide, on how monsoons are changing here. I mean, it's not my place to be talking about monsoons because it's a fascinating area of discussion. And I would actually recommend that you invite somebody like Roxy Matthew Call or somebody like him to talk about it, because he knows this space so much better, and how it's changing. But the point that I'm making here is that you've got a gradient starting with a very high amount that falls around the Gudalur area, right? I mean, this would be the area of maximum impact of the receiving the most precipitation, right? And you have the intensity of land use. I think this is something that everybody knows about, right? Then let's look at where is the wetness. Who retains which landscapes within the larger province retains more moisture? Now, having looked at these 6 parameters, we would imagine that the wetness should have also changed a little, but it's more or less quite uniform. The soils tend to absorb the same amount of moisture, and they're pretty much stable. But here's the problem, that if you start looking at 2 variables together, it makes it more interesting. Now, for example, if you look at the power of the streams, as you know, in summers are ebbing, they are very low in their power. But in monsoons, just now perhaps, or a little earlier, were in full flow, right? So if you were to look at the power of the streams, you notice that the power is highest in areas that are marked dark blue. There are only some places here and there's some places here, right? And the areas which receive a lot of monsoons do not have as much power as that we imagine they should have. That's perhaps because the density of streams may be higher. Let's look at this. So if you look at, okay, I should have put streams here, but okay. I want to talk about another thing called lineaments. Lineaments are basically faults and slips that occur underground, right? Because there are cracks in the earth, in the bottom of the basement rock, how they have cracked over time. So these are lineaments. Most streams follow this pattern. They actually like to take the path of least resistance and flow in an area where it's not going to encounter too many physical challenges, right? Now, this is where the stream, the distance of any place from any stream. So if you look at the lineament map and this map, it tends to have the same patterns. Look at these, for example, these green lines here. They tend to, kind of have a pattern with in which they flow. So what this is trying to show is that any distance which is close to a stream is 100, 200 meters away from one another. So the intensity and the size and of the flow and the distance of any piece of land from a stream. And finally, what is a marker of infrastructure development, a stable marker, is a road, right? So if you look at roads as a marker of how much infrastructure, or how much of the earth has been worked and reworked, you look at this, you see that the very few parts, perhaps only in the north where it's not as much, but look at this. You've got a huge concentration of earth being worked and reworked. Whether you're making a house, whether you're making a resort, or you're making roads, the concentration is this. Now, from 1998 to 2016, one study looked at where does all the landslide occur. If you were to map it, ideally, logically, because of high rains in the west, starting west of Gudalur to down here, you would anticipate because it rains there more, it should have more landslides, but it's not so, right? There is a concentration here. Now, this is, of course, the more dense part of the of the district. It's the soil has been reworked. You've got a high density of road networks. But there's also another factor. You look at the factors that were shown earlier. If we were to make a common index of the 9 index that I showed you, lineaments and stream distance and all of those, then when you put it together, this is what it should have been in natural terms, the intensity of landslides. But look at this, the actual intensity is here. So we are doing something wrong. We are moving Earth in places where it should not be moved, right? Okay, now just a case study. I think this is a very famous case study. I think most of you know this. It was a tragedy that could have been avoided had town planning been better, and many other considerations were made. For those who don't remember the tragedy, let's just jog our minds. So basically, along the NH 181, there were houses and railway tracks and everything that got inundated by a landslide, a massive landslide. In fact, there was not one single landslide. There were multiple of them that happened almost in the same, in a very close period of time. Now, what had happened is that the first set of rainfalls that took place occurred over 8 months, and they were not as sharp as one would imagine. In fact, that year, 2008-9, was not a heavy year in terms of rains. It was a very strong El Nino. But towards the end, it became a La Nina. It flipped. And you had massive amount of rains in just 10 days. The same amount of rain that happened over 8 months happened in 10 days, right? Now, the logical thing that we assume is that it rained too much and therefore the land gave way. Yes, it is. That's true. But you know what the point here is, that if somebody was measuring the saturation, what is called the soil rock interface saturation, you would be able to predict when the soil is going to give way. Because soil mechanics and soil and rock mechanics is a very advanced science which we don't practice. We would be able to tell when will this rock and soil system not be able to take the weight of the road or the houses or whatever stands over it, right? What is the collective weight? What is the carrying capacity of the soil and rock, like Dr. Sukumar spoke about in this morning? So I think there is a carrying capacity for the rock also and the soil system, which we don't appreciate, right? So the strength of soil and rock together is something that we don't look at. And therefore, we end up making lazy judgments about landslide happened because it rained. It rained everywhere, but the landslide occurred just there. Why? That's the question that you should ask. So basically, the point that town planners, even architects, landscape architects, infrastructure developers should look at is the soil rock interface. Most of the infrastructure development that happens looks at only the top surface. If they're putting a pipeline, they will only look at the surface on which they're setting their pipeline. The challenge is that you have to start looking deeper, because that's where the movement of water and soil and all of that takes place. One important aspect that you should consider is looking at what is called pore water pressure. I should have put it in the same line, I'm sorry. So it's pore water pressure, because that's the one that if it exceeds a certain amount for a certain soil, it is sure to give way, right? Now that's something that we don't do at all. Okay, I want to take you to something that geologists know but are never consulted about. Now it looks like a very pretty map. This is WDC, means Western Dharwad Craton, Central Dharwad Craton, and Eastern Dharwad Craton. This looks very beautiful, right? And here's the sea, right? Now this is an area. Okay, don't go by the markings on the right, because I don't want to talk about geophysics, and I don't know it enough myself. Let me be very clear. But what this map is trying to show is that the intensity of gravity is never uniform in a place. Now, because the thickness of remember the basement rock, which I said was anywhere between 25 to 40 kilometers deep in the Nilgiris. Now, towards Udupi or towards, say, Kerala, which is a younger rock, it's much less because the mantle there, the crust there is extremely thin compared to the Nilgiris. Nilgiris ideally should have a gravity which is around much higher, right? So these kind of maps are called the Bouger's gravity anomaly maps or gravity maps. Now they are basically what geologists call a geological X-ray. So they have these machines which they go and use. It's like a color Doppler. If anybody's been to a hospital, I hope you never go to a hospital, but it's like a Doppler. It actually looks at how your organs are doing inside by looking at penetrating your tissues and trying to look at what's wrong with them, right? If you have a cyst, if you have a melanoma or whatever, sorry, I should not get there, but if you have cavities or whatever, right? So it tries to tell you what lies beneath. Ideally, there should have been a very good gravity map for the Nilgiris. In fact, for every region, for Dharali, we should have had one, right? For Kathua, we should have had one. For Kishtwar, we should have had one. We don't. Now, the two agencies that are responsible for it are actually global pioneers, but we've never leveraged them. The West has learned from us, taken it, refined it, and are using it. Okay, but we don't do it. The point I'm making here is that we expect the Nilgiri, because of its thick, below the ground iceberg-like situation where you see only the top, which is above the ground, but below the ground it's much bigger. The mountain that's hidden from us in our plane view is actually much bigger, right? But it has a lower gravity than what it should have had, right? That's because the Nilgiri hills appear to be floating on a deeper crust. It is an accretion. It's a collection of croutons that are floating on top of a thick soup. Okay, so that gravity is not as much. Okay, but what the point here is that because of its thick crustal roots, there is a significant amount of stability, but as you come up, that crustal stability is compromised. Now, what we need to remember is the Moyar, for example, or several other shear zones that exist here remember there were oceans that closed down, and I said that hydrogen and oxygen based minerals are formed, and the Moyar rocks are slightly different from those in the Nilgiris, right? You remember that part when the ocean was closing? Remember that part? Now that's where this is, that you've got places like this where the gravity is very, very different from the gravity that is here. Now, why is gravity important? You ask. Now, the gravity is important because we want to look at how the cracks and the lineaments have arranged themselves. And that, if we understand, we would be able to understand how we want to plan our infrastructure. Because if one lineament moves, it creates chaos. You see entire buildings sink down because the lineament has moved only a millimeter or half a millimeter. And that's enough, because that's the power of the earth, or the deep-seated power of earth. Okay, I just want to look at what is it that we know about landslides, particularly for this region. I think this is very critical for everyone. Now, although we are in the Dodapetta area should be the most landslide prone, it is not. Right? Everybody would imagine that there's more rain there and it's exposed to rock and whatever. Therefore, it's more prone to landslide. Sadly, that's not how it happens. So if we see, it is the most places that are in the northeast or southwest aspects are the ones that have soils and rocks that actually favor creation of landslides. It's not universal across this region. So town planners have not considered this as a factor. Now, lower slopes, strangely, are more prone to landslides here rather than the steeper landslopes. So Nilgiris is a very contrarian place in that sense. right? The third condition, remember when I was talking to you about that friable rock, the one which was shiny, right, with the limestone in it, that's the one that is most susceptible. So if you look at the landslides that have occurred and you go and examine the rocks, the cross section, you would notice that they're largely in these regions, right? And it's more prone in ridges, not in valleys or in steep hills. It is the ridges where you have the problem. Um, and most of these landslides occur within the 500 meters of a lineament. So if the lineament had been mapped well using gravity maps, you would be able to know where to construct a larger, uh, you know, infrastructure thing, or maybe you would break them down and make smaller ones, right? A very short comment on monsoons, because I want you to invite somebody like Roxy, Matthew Call, or somebody to talk about monsoons. Nilgiris in particular is very susceptible to what's going to happen in the future in terms of monsoons. Now, monsoons is measured in different ways. The most easy way, of course, is to look at how much fell in the last 24 hours, right? That's one. But there are other ways in which it can be measured, and they're very effective. Stream discharge or rainwater discharge in rivers is another very good metric, because you can see the collection in an entire watershed and whether the flow has changed over time or within a certain season. It's a good metric, but all of these give very diverse results. So what is the metric for plains? What is it for valleys? What is it for the hills? I think that's something that we have to start looking at in terms of water security, soil security, and relating it with monsoons. That's a very important aspect. I think if you were to put like they say about economists and lawyers, if you put two monsoon experts together in a room, times are when they don't agree with each other, even for the same locality. And that's very important, because we don't have a clear understanding of the past or the present, and certainly not about the future. But there is one consensus which is very, very clear. We know that the Indian summer monsoon is changing. It's getting intense in some places. It's getting less intense in some places. And we know that as of now, there's a 3% increase decade on decade, but we don't know when that decade would end, right? And Roxy has written a fabulous paper saying that, the central peninsular area is going to have a depleted monsoon by 2035 or 2050. And the region between Narmada and Tapti is going to be the one that would be getting a lot of rain. The last we saw this happen was in 1780s. And that's one reason why the port of Surat was collapsed and the rise of Bombay happened. Because the floods that happened in the Tapti choked the port of Surat. And that phenomena is going to happen again, according to what Roxy is saying. If that happens, there's going to be a huge amount of siltation in the Narmada and the Tapti. But with respect to the Nilgiris, you're going to have a very depleted monsoon here, if that happens, because there's a shift in band. Which area is going to get more rains, which are going to get less rains, right? Okay, I'm just going to show you one last cartoon. This is from Roxy's paper, 2017. It's a very interesting, illustration that he's made. Now, what he said is that, if you were to look at periods before, in early industrial age, if you were to look at how the monsoons were behaving, the normal monsoon was when the oceans were cool, the oceans hadn't warmed themselves, and the land used to stay warm. You had a very hot summer and an ample monsoon. So you had something which was a normal monsoon cycle. I mean, I don't know, there's no term as a normal monsoon, but every landscape would get its fair share of rains. But from the 1950s, the ocean has become warmer. That's because of acidification and more anthropogenic greenhouse gas emissions. And the land has got cooler. And as a result, the arrows, if you notice the arrows here, that the cool ocean is sending in monsoons here to the interiors of the Indian subcontinent. This has reversed the air system. And what is happening is that the peripheral areas are the only ones that are receiving a lot of monsoons, if at all. And the interiors are not getting as much rainfall. So Marathwada, Vidarbha, all of those became very, very dry since the 1950s. Okay. Now, this may appear that there is a revival of monsoon. But what has happened is that the ocean, instead of having turned tepid warm, has now turned strongly warm. And the land has turned warmer still. So while this may have looked like a revival, it might resemble the same cycle that you see here. It has also increased the variability of monsoon in terms of places within the Indian Peninsula region. And that is the danger. It looks the same. The term here that Roxy uses is revival of monsoon, which is correct. But what he also warns us about is that if you notice that the peaks have turned red here instead of the usual yellow, and he's put in a different color to warn us about the fact that the monsoons are going to be extremely variable within the country. Now, I'm just going to summarize. Okay, why do I love the Nilgiris? I mean, actually, I love every landscape, but why particularly the Nilgiris? I think it has a unique geology. If you were to ask me to pick up 3 or 4 from the Indian subcontinent, I'm sure to pick up one of Nilgiris as one of the places. And I'm surprised there's no geological museum here, or even a small display of the wonderful rocks that you find here. I wish somebody did that. And it dictates regional climate. I mean, if Ooty did not exist or the Nilgiri Hills did not exist, Bangalore would not be called the air-conditioned city. Right? A lot of these regional patterns that you notice, or Mysore or Mandya, the unique agricultural, or Raichur for that matter, a very important place for rice production, would be very different. Right? Of course, I think Professor Sukumar spoke about this very clearly, so I will not harp on this. I think, one of the things other than, the Vindhyan connection, or what Sundarlal Hora spoke about, which I think is not a very valid theory anymore for amphibians and fish, but for Nilgiris, this is very important in terms of small mammals and plants, especially flowering plants, that it remains one of the areas where you see forced speciation. One of the unique things about the cloud forests, about which I hope Robin's going to speak about, is the creation of these small habitats which are putting in that additional pressure of speciation, which is very, very interesting. And I think I think again this is something that Professor Sukumar and earlier others have spoken about quite clearly. So I think all of this taken together makes the Nilgiris one of the most fascinating places in India and perhaps the world. So thank you so much. Yeah, there's a paper that came out last week by Professor Murugutade from IIT Kanpur, where he's talking, and I think he revalidates what Roxy is saying. See, Roxy wrote a paper on Central India, and Professor Murugutade says that there is desiccation that's going to happen, or intermittent desiccation in Southern India. So I think that's what, I think if we read both the papers together, I think they kind of complement one another. Arabian Sea cyclogenesis and Arabian Sea warming is a very interesting thing. If you notice, 15th century to mid 17th century, at the peak of the Little Ice Age in the Indian subcontinent, there was an equal number of cyclones on the Bay of Bengal region and Arabian Sea, which whittled out around 1800s. But the pickup of the east, starting with Koringa and many other large cyclones that happened, was around 1780, 1790, right? And since then, you've had only very large cyclones in the eastern part, right? And the Bay of Bengal has warmed up, as you know, much faster than what the Arabian Sea has. So, and of course, that's got to do a lot with the silicate cycles. And I don't know if you've read the end note in Indica, which actually talks about it. In my book, Indica, I've actually said, why does the eastern part of the peninsula or Bay of Bengal get more cyclones than the west part? So I kind of tell you why that is. The best way to climb a mountain is usually not the straight way. So if you look at even elephants, they go a zigzag way. That's one, to conserve energy, and two, you make faster progress if you're going like this. And think about it. If you had cars or carts in those days, or even horses, and you've got somebody on the horseback, going straight up is a problem, but going along what are called contours, as they go gently around each other, so it's always zigzag. So cutting across contours is more energy efficient rather than climbing a hill. Yeah, okay, great question. So again, in my book, I talk about why the Palakkad cap was created. And that's because when Madagascar and India were joined together and they started to unzip from below, there was a part of that hill that went into Madagascar. So if you look at Madagascar's map and look at Kerala's map, there's a hill which is exactly the same shape as that of the gap. So it's like a jigsaw piece. And that got pulled by this suture that was separating. Like I said, we have the technical expertise, and, we don't leverage the technical experts to give or share this information with town planners or with infrastructure planners. Now, the NGRI report, for example, the National Geophysical Research Institute in Hyderabad, they have some fascinating data on not just the Himalayas, but also for parts of this region. I don't know whether they have specifically for the Nilgiris, but they are supposed to share the data on how the hills are, how stable are they, and which parts of the hills are more stable than the others, and whether infrastructure development can, the pressure of infrastructure development of the scale that is being proposed can be taken by these hills. And I don't think we consult those reports. What we consult is hire a consultant, get an EIA report done, which of course is so easy to get done. And so it's much of it is eyewash. And I wish this was questioned in technical committee themselves, that why have you not consulted the NGRI reports or NIO reports or any of those technical body reports or even scientific papers. The graphic that I showed is from a paper, right? Now we need to have a better microscopic micro level map of that for the Nilgiris, that where are the bumps in gravity? They're not so uniform, right? Where are the lineaments? I think the lineament map that I showed you is actually very crude. It has to be much finer. Only then we would know where's the gully erosion, where's the risk of gully erosion, or where is the risk of subsidence of the land? Where is it going to collapse? It looks very stable now, but it will not be stable, say, 20, 30 years later. That's the challenge that we have.